Hello, everyone. Welcome to week 10 of distance learning. This will be my final video for you, um, and it'll be our final full week of school for the rest of the school year. So we can consider this, we've made it to the end. Distance learning has not been easy for anyone, but we finally made it. Um, Next week, there won't be any lessons, there won't be any kind of distance learning activities to do. The only thing that I'm going to do, because technically Tuesday is the last day of kind of not of school, but of distance learning, we're going to try to find some time between the beginning of the week when we can all meet, kind of pull everyone in, as many people in Algebra 1 as we can, and find a time when we can all meet and kind of give a send-off for the end of the year. So let's get into this. I spent some time trying to think about what am I going to do to end this 2019 to 2020 school year. In these conditions, no one wanted to end it like this, right? But what could I do to kind of to end this in a relevant way? And I thought that I would do this activity, or I would do this lesson with you about COVID-19 or coronavirus, and its growth. Um, and hopefully its decay as we move on into the summer. So come with me, and again, I hope you all had a great weekend. I hope everyone's feeling well. Um, my heart goes out to anyone who's been impacted by this more so than the rest of us. But yeah, let's get into this. So I'm going to use Cami here. I'm going to write my name. Let's see, Mr. Doobie, using green apparently. And what I'm going to do this week is I'm going to go through this lesson with you in this video. I'm going to try to keep things not too long. Maybe I'll break it up if I have to. I probably will have to. You know me. Um, and then I'll just post some Google form questions based on the notes that I take in here. So you can either answer those questions as you go through the video, or you can just take a look at my notes afterward and answer them that way. But hopefully you guys are joining me for this video. I know my videos have been long, probably a little drawn out. But I mean, that's how I do things, right? So let me read this for you guys. On January 21st, the first person with the coronavirus, or COVID-19, was confirmed in the United States. The way things went in China, the number of people with COVID-19 doubled about every 3 days. Every 3 days, the number of people infected doubled. A U.S. medical expert, you may have heard this name before, named Dr. Anthony Fauci, warned the president that what happened in China could also happen here soon. Um, so, 3 days later, on January 24th, after having one person infected on the 21st, 3 days later, kind of just on schedule, there were 2 people infected with COVID-19 in the United States, both in the state of Washington. And by day 6, so January 26th, or I guess it would be 27th. I can do math. There were at least 4 confirmed cases, and I think there were actually 5. So this whole doubling rate, maybe I should underline that. This doubling every 3 days that happened in China did also happen here, just like our medical expert warned us. And just to kind of tell you guys, I'm going to be looking at some data from the CDC, which is the U.S. government Centers for Disease Control and Prevention. I'm going to look at some data in this lesson today. So you can go out there and look at it too. If you go to cdc.gov, you can easily find information about the coronavirus. And so the virus spread without mitigation, right? Even though we had warnings, we had a lot of data coming from China, about the rapid doubling rate of this virus. We didn't do anything about it at first. What does mitigation mean? It means that eventually, right, schools and places of work were closed to try to limit the number of people who were interacting and exposed to the virus. We started social distancing. We did this, what's been tough for a lot of people, not seeing friends, not seeing family, um, not traveling, not going out in public. So we did all this social distancing to help mitigate this spread, right? Social distancing. But let's see what this simple model of growth of doubling every 3 days means. What does it predict? So here's a table. We can say here's the total days since January 21st, since day 0, we can call that. Day 0 is January 21st. And we said every 3 days, the number of people infected doubles. So if on day 0 there was 1 person infected, 3 days later, right, this is January 24th, right? Well, that's 1 doubling period. So we can call that, every 3 days is going to double once. So then we doubled this, right? So we went from 1 to 2. In other words, we multiplied this by 2, this number. And on day 6, which would be January 27th, that represents 2 periods, 2 3-day periods, right, of doubling. So then this number doubled again. And we had about 4, I think it was really 5 people infected with the virus. And so this happened again and again. Let's see. So day 9, day 9. That's 3 3-day periods, right? Each time this goes up by 3. Um, and we say it's doubling again. So then we doubled again, and this number multiplied from 4 times 2 to 8 people infected. What happens after that? Let's see what this. Let's actually do what this says down here. Fill out the table. What happened on day 12? Well, day 12 means we had another period of doubling, because it's another 3 days. So how many people were infected then? Well, we multiply by 2 again, and we had 16 people infected, right? Multiply this by 2 each time. How about on day 15? How many doubling periods is that? Well, that's another one. So this is going up. Now, the tricky thing here is that this isn't the days, right? These are the days. The days, we're just counting up by 3 each time. And then because every 3 days we're going to double this again. Now this is going to be 32. 16 times 2 is 32. And if we continue this table, let's do it a few more times. So let's see. Each time here we're adding 3 days, right? So what was the next doubling period day? It was day 18. And you can see, these numbers, they're kind of growing, but not, whatever. 32 people in the entire United States isn't huge. But what happens on, let's keep going by 3 here, by day 27, let's go by 3 again, by day 30. So after 1 month of the virus beginning in the United States, how many doubling periods is each of these? So remember, this is going up. Every 3 days, this is going up by 1. So that represents 10 doubling periods, right? What are these numbers? What happens with these numbers? Well, we said these are doubling every 3 days, right? So every 3 days, this multiplies by 2 again, right? So on and so forth. as they say. Let's see, can I multiply 32 by 2? I could. I could go to Desmos here, and I'm using the scientific calculator, desmos.com/scientific. You could do this too, and you can just use it as a calculator. 32 times 2 gives us 64. So there's 64 people infected now, and then times 2 again, right? 64 times 2 is 128 people infected. And this is just like a very basic model, right? It's based on this whole idea of doubling every 3 days. Let's do it a couple more times, and then 256, right? And 2 more times. 256, 512, 512 times 2 is 1,024. So quickly, after a month of the virus, we went from 1 person being infected to over 1,000 people being infected. And what does this look like? Well, if you took all this and you graphed it, this is the picture that you get. Here's our graph, right? Of those number of people infected, and this is 3-day periods. So we went through 10 3-day periods here. And as you can see, we were at over 1,000. Is this a linear function? Is this function linear? Let me see if I can connect the dots here. Well, you tell me, does it look like a straight line? No, it's definitely not. No. We can look at it in 2 ways. There's 2 ways you can tell if something's linear. One, if the graph makes a straight line, then it's linear. It's kind of the name, it's in the name. And 2, linear would mean that it's increasing, it's adding the same constant amount each time. But we're not adding the same number each time, right? Instead, we're multiplying by the same number each time. No. So that's actually not linear. That's not the hallmark of a linear function. That's the hallmark of an exponential function. So I could say no, because the graph isn't a line. And in fact, you can see what happens to this graph. It starts off very, very small increases, but then very quickly it rises, because soon after 1,000, we're doubling that, right? And if you double 1,000, now you're at 2,000. And if you double that, now you're at 4,000. So you're increasing by by larger and larger numbers each time. I'm going to write here instead, it's exponential. And by the way, I'm kind of taking this. Mr. Cohen did something like this a little while ago, and I thought it was a really good way to talk about exponential functions. So this is an exponential graph. You can see because the hallmark of an exponential graph, like I said, is we're multiplying by the same number each time. Could we write an equation for this function? That's an interesting question. What would our equation look like? I already filled out the table. And by the way, I'm not lying to you guys. Like, if you want to take a look at this data, you can see at the very beginning here, in January, we had this. This is the number of cases by day by day, new cases, and you can see that it started off. We had one. Where did the first person? They said actually it was here. I don't know. This is a little different data. About the 20th, 20th or 21st day, we had the first person. And you can see like the number of cases didn't grow very quickly, day by day, but then very quickly, just like on our exponential curve, it shot up to, soon we had 1,000 cases a day after only, a couple of weeks, a few weeks. I guess that's about a month later. But then very quickly, after only another week, we had over 10,000 cases a day. You can see this exponential growth curve at the beginning of the virus. And this is about the point when we left school, right about here. I think it was 313 is when we closed the school. And you can see why, because this is dangerous. This is really scary. A growth curve like this that increases exponentially. Let's write an equation for this function. So how could we do that? Well, what's a simpler way than just multiplying by 2 each time? For a general exponential function, this is the form that they come in. Y equals a times some b to the power of x. And this is what makes it an exponential function. The x is in the exponent. What do these numbers represent? A is representing the that we're starting with, our initial value, our starting value. It looks a little strange, but you get what I'm saying. This is our starting value. And B here is called the growth factor. It's the number that we're constantly multiplying by. You can see it's times b, times b, times b, times b to the power of x, because we're just multiplying by b over and over and over again. So if we were going to try to model this growth right here, this data, with this kind of function, what equation would we write? We would write y equals, well, what was our starting value? We started with one person, right? One person. And then what did we do every 3 days? What was the growth factor? Oops, I forgot to write factor. What was the growth factor? What was the number we kept multiplying by? We kept multiplying by 2, right? Because it kept doubling. So our growth factor here, maybe I'll do this in green, is we kept multiplying by 2 to the power of x. That would be a simpler way to do it than just in our calculators, take the last number, multiply by 2, multiply by 2, multiply by 2 again. Instead, we could have just said how many 3-day periods were there and plug that in for x. So x here represents how many times we've doubled, how many times we've multiplied by 2. This is the number of 3-day periods or times we've doubled. So how many times doubled? I can write. How many times have we multiplied by 2? And so instead of doing this 10 times, we could have just said, oh, it's 1 times 2 to the power of 10. And if you do that in your calculator, you get the same answer as what we had before, 1,024. So this is a much easier way to do it with this exponential function. 1 times 2 to the power of x. 1 because that's what we start with, times 2 because that's what we're doing. We're doubling. How many times have we doubled? All right. Maybe I'll stop there. That'll be a first part, and then in a second I'll do a second, maybe a third part. Keep these videos short.